Today I want to talk to you about waves. We are starting to study chapters 10, 11, and 12, and that has to do with waves, the function of waves. It also has to do with sound waves and electromagnetic waves, and there is a difference. So when you look at the different properties of the waves, if you will notice that a wavelength goes from that top hump to the next hump. We call those humps the crest. The part at the bottom we call the trough. This is actually a picture of a transverse wave. And when we are determining what a wavelength is, we go from the top hump that we call a crest, or you go trough to trough. And you can measure that and actually determine how long a wavelength is. If you'll notice underneath the picture, it says a wavelength, and then it has a Greek symbol there. Anytime you see that Greek symbol, that stands for wavelength. And the wavelength, the definition it gives you, is the distance between two consecutive peaks, crest to crest. When we talk about amplitude, if you look at the picture and you see the dotted line that is going across, that is what we call the equilibrium position or the equilibrium point, or it's also called rest. So when you measure from that rest point, that dotted line, to the top of the crest or to the bottom of the trough, that is called amplitude. It's the scientific way of saying basically this is how much energy a wave has. So we call from rest to crest amplitude. When we talk about a wave period, we are talking about the time it takes for one wave to pass an observer. So if you look at the picture, you'll see that we have wavelengths, and then it shows you what the period is. At the top, notice we're measuring that wavelength. That's the time it takes for that wave to pass you as the observer. So if we count the number of crests in this little bit of time, you've got 1, 2, 3, 4. Look over to the right, and that shows you that it actually has a frequency of 4 hertz. Then if you look at the one on the bottom, and you will notice that we've now used our symbol for wavelength, you'll see that the period is much smaller. And if you count the number of crests, 1, 2, 3, 4, 5, 6, 7, 8, you'll see that the frequency for that wave is 8 hertz. If any of you happen to ever listen to the radio, and let's say that you dial into classy 97.3 megahertz on your FM dial, what that's telling you is that 97.3 waves pass a point every second. And so you are actually tuning into a wavelength when you tune into K-Bear, when you tune into Classy, when you tune into any radio station or television station, you are tuning into a certain wavelength that is sending that information to you. And this is one way we find it. Also make sure that you notice down at the bottom underneath the picture where it has that capital P. That is the symbol that we use for a wave period. And once again, the definition is, this is the time it takes one wave to pass the observer. So we want to also talk about frequency. Okay, when you talk about frequency, notice at the bottom we use a small f, and that's the number of waves that pass a given point in any second. So once again, we've got our pictures here that we used in the previous slide, and we see the frequency for the top wave is 4 hertz. Notice hertz is actually the unit for waves. And then on the bottom one, we have 8 hertz. So why do you care? And why does this matter to you? Well, when we need to talk about frequency and periods of time, you use them every day. Maybe you just haven't used the terminology that we use in science. So here's a question for you. What is the frequency of the second hand of a clock? Well, think about it. Second hand of a clock. What does a second hand of a clock do? We all know that a second hand of a clock counts off every second of a minute as it goes around the clock. So when you want to talk about frequency and period, you would say that the frequency of the second hand of a clock is one cycle, one time all the way around every 60 seconds. And what is the period? 60 seconds. So here's another question. What is the frequency of the United States presidential elections? Well, think about it, okay? We have presidential elections every 4 years. So our frequency would be one election every 4 years. And the period would be 4 years. So hopefully this will help you to put it into context and think a little bit more about period and frequency when we're talking about waves. So when we talk about the symbolic form, to figure out, and we use frequency to figure out how much time does it take for that wave to get to us. That's how we know what the speed of sound is. That's how we know what the speed of light is. And like any mathematical formula that we use in physics, it can be manipulated. So if we want to find out the frequency, but we know the time, this is how you would manipulate it. So when we talk about wave motion, speed, and type, if you look at the picture at the bottom, you can see there's several different things going on there. And what we need to remember is that when I say wave, most of you probably think of a water wave. That's not really what a wave is. We've called it that. But a wave is just a transfer of energy. And a wave has to have, at least transverse and compressional waves that we're going to be talking about, have to have some kind of medium to be able to move. So in water, a wave is actually the energy, and the movement you see is just the water moving, but energy is actually all that a wave is. Right now, as you listen to my voice, there is a medium that is transferring the sound of my voice to your ear, and it's all the air particles that are captured in this room. So as I speak, my voice goes from air particle to air particle to air particle to your ear. Now, if we were able to completely seal this room and we sucked all the air out of it and we actually made it a vacuum, before you died from lack of oxygen, I could stand up here and talk and talk and talk, and you would never be able to hear me, simply because there was no medium, there was no air particle for my voice and the sound wave to be able to move on. So I've got all this sound coming out, and you wouldn't be able to hear anything. So transverse and compressional waves require a medium. Now this is basically, on this slide, showing you how to figure out wave speed. Notice we've got frequency, wave speed equals frequency times, remember what that little symbol stands for? Wavelength. Pretty simple to figure out. So anyway, you go on and you read the same type of wave moves at the same speed regardless of the frequency or the wavelength. And then it talks about being inversely proportional to the wavelength. Okay, so let's think about that. Let's go back and look at our picture that we had before. Maybe if we'll get back there. Okay, when it talks about being inversely proportional, we are talking about the fact of if the wavelength is shorter, like the one on the bottom, do we have more or less waves? We obviously have more. The frequency is greater. So if we have on the top, if you have a larger wavelength, you have less frequency of wave. It's kind of a no-brainer, but this just gives you a picture so you can think about it. If there's more waves, the wavelength is longer. If there's fewer waves, the wavelength is shorter. So that's what it's talking about when it talks about the fact that we have actually frequency and wavelength are inversely proportional. That's what it means. When one goes up, the other goes down, and vice versa. So when we talk about wave type, we've been talking about transverse waves, and all the example I've given you have been transverse waves. And transverse waves, if you look at the top of the picture with that slinky, up and down, up and down, up and down, that is a transverse wave. Now a longitudinal wave, or we call them compressional waves, is the example at the bottom. And this example at the bottom shows you how the wave on the bottom, the compressional or longitudinal wave, the wave moves back and forth, back and forth, back and forth. Notice the transverse at the top, it will actually follow, and it'll go up and down. So that shows you the difference. Now notice we've got wavelength mentioned here. So you notice we have on the top transverse wave, trough to trough. That gives you a wavelength. But on the bottom one, what's going on? Well, a compressional wave doesn't per se have a crest and a trough. It has places where we call them compressions, okay, which is where it's really tightly put together. And then it has places where it's spread out, and we call that rarefaction. So what we do on a compressional wave or a longitudinal wave is we mark from compression to compression or from rarefaction to rarefaction, and that will give you the wavelength. So that ends up your introduction to waves, and we'll do some work later on in the week, and I hope you enjoy all that we're going to be doing with waves, because it's a lot of fun and we have a bunch of fun demos to do. So have a good day and work hard.